Hey guys, welcome to the sixth lecture of the modeling part of the course. Here we're basically going to implement the forward propagation part of the models. There's a few variables to initialize. We're going to set up the loops that are going to go through the different images and then that are basically going to train the network, making sure that the error decreases. So there's a few more things we need to do before we start writing the actual loops themselves. We're going to create a counter called J, and that's going to be initiated at 0. And then we're going to have our success rate, which is going to be equal to 0 to start with. Okay, so really horrible success rate to start with. And then we're going to have this error variable. I mean, we'll do that later, that's fine. Okay. So why do we need this? Because we're going to create a while loop that looks at the absolute value of success. So in case that's negative, we're making sure we're looking at a positive value so that we bound it properly with our condition. And we want to make sure that this loop we're creating right now keeps running again and again as long as our success variable is basically below 99%. Okay. So until we reach 99% success when running the neural network on our training set, we're not stopping. So obviously we're not going to reach that. That's like crazily accurate and would require, insane optimization, but we can use it to run it long enough that at some point we can look at the success and be like, I'm happy enough with that. I can stop the algorithm and use the results I currently have. So we want to use the counter J that we just initiated through each of these iterations, right? So these iterations are not going to be the ones that go through each image. They're going to be the ones that basically update the weights, updates the learning rates, updates everything for the model to run again on a new training, like on the training set again, and then re-forward propagate and then redo all the gradient calculations, change all the variables and try again and try again. And at the end of each of these loops, we're going to calculate our error and success rate to see where we're at, and we keep going or we stop depending on how good we're getting with our neural network and how well it's currently being trained. So I'm just going to initiate all the variables that we'll have in this loop for later. I'm just going to do all the gradients and the matrices now, so it's done for later. But I mean, you've seen all this in the lectures with Albert, so you should remember this. So first of all, we're going to do the gradients for the bias in the hidden layer. That's going to be delta B equals zeros H layers 1. So this is going to be, the first one is going to be delta B is equal to 0. So we're creating a matrix of zeros, and it's going to be with the number of nodes in the hidden layers in terms of columns and of rows, and in columns we're going to have the number of hidden layers. So that's quite straightforward because, as you know, we have a B for all the hidden layers, so that's the bias for all the hidden layers, and obviously there's the number of nodes in the hidden layers. I mean, that's quite straightforward to get. Then we're going to look at the gradients of the weight matrix of the output. Again, we're going to do a 0. We're going to create a 0 matrix, and that's going to be zeros of the number of output nodes times the number of nodes in the hidden layers. And then we are going to do the delta. I'm just going to copy paste that every time it's easier. We're going to do the gradient for the weights in the layers, so delta WH, zeros up. That's going to be same number of nodes at the output and the input, but this time we're going to do that by the number of hidden layers minus 1. It's basically the same thing as we saw for the weight matrix itself. Obviously, that's the gradient for these weights, so it's going to be the same matrix because each gradient corresponds to one of the weights in that first matrix. Then we're going to do the delta W input, which is the gradient matrix for the input weight matrix. So input, and here we have the output is going to be nodes, the number of nodes in the hidden layers, and then the input is the number of input nodes. Okay, then we can keep going. We're going to have, we did delta B. Let's do delta B output here so it's all together. So up, and that's simply going to be a single column of output nodes, and then we just have one. So output nodes one. And the last thing I'm forgetting is I want to initiate as well the actual output of each node. So that's going to be zeros, and that's going to be the same because it's for the hidden layer. Obviously, it's going to be the exact same as the biases. Zeros, not H layers. All right. So if I do mistakes and so on, obviously when we run it the first time, we'll be able to see what's wrong. And because we're going to use the error, I want to update, make sure the error every time we start again a for loop on the training set. On all the images we have to train the network and do one pass on the network, we need to make sure we reinitialize the actual error that we're calculating to 0. So the initialization is done. Now we can create the for loop that's going to go through all the images. So let's say I, that's going to be our counter, equals 1 to, it goes from 1 to the number of images we defined earlier. As you saw, we defined that right here. So that's how many images we want to have a look at in our training set. Okay. So, I mean, we can look at the first, like that's just going to say the first 60,000 or the first 1,000 or the first 2,000. But basically, we can also look directly in the matrices we import, and we can actually like just take the, you know, the first, like from the 1,000th to the 10,000th, from the 10,000th to the 60,000th. I mean, we won't do it here, but it's very easy to do. And, you know, it wouldn't change much because it's a big number of pictures and it kind of averages out the performance, but you can do that as well. You can just look at specific parts of the image matrix. So let's keep going. So we're going to define the output layer so that the output layer we actually want to get, right? So that's based on the labels. And that's basically the ideal result we want. And that's the result we're going to compare our neural output layer to. So we're creating a 0 matrix as well. Output nodes, 1, of course, because the output layer. And then super straightforward, we're just going to say that at each iteration, for each image, we want y. So that's basically a matrix, right? That's a column vector of that has one column and then as many rows as output nodes. And we just want to say that we're going to look at the label, okay? And because the label can be from 0 to 9, but obviously in Matlab, when you call matrices, you can't use 0. Like you can have an index that's 0. You need to have from 1 to plus, whatever, to infinity. So here we're going to say, you're going to look at the label of that image, and you're just going to say that that label plus 1. So if it's 0, it's 1. If it's 9, it's 10, basically. That's going to be the row we're looking at. And obviously, we still have one column. So it's going to be labels I plus 1. So we're looking at the label matrix. We're looking that label for that picture, you know, so we're looking at the label, let's say for picture like 1 or picture 20 or picture 20,000 as it's here. What's the value of that? Okay, and then we're adding 1 to that, and that's going to be the location in the Y matrix where we're going to say that it's equal to 1. Okay, and all the rest will be equal to 0. So our output looks like everything is 0, but the index, but the position where our actual value is at, right? So if the label value for that image, if that image is basically a 9 that's been drawn and therefore the label is a 9, then in our Y output matrix, we're going to make sure that the 10th position is 1 and all the others are 0. So that's our output layer, and now we're going to do our input layer, which is going to be full. So we're first going to go through, as we said, we're first going to do the first row, and then we'll do, we're just going to define the row, and then we're going to do all the columns within that row, and then go on to the next row, do all the columns within that row, and so on. So the way to do that is to have two nested for loops. So let's define the counter row equals 1 from 1 to size of images 1, so the amount of rows, and then we want to do that for column equals 1 to size, sorry, 1 to size. Can I just put that? And that's going to be the amount of columns, so that's going to be the second dimension. So we actually want to define our input node matrix based on the data in our images matrix. So to do that, we just need to go through all the pixels in the images and then write them up accordingly in a single column vector in our input nodes. So we have as many input nodes as we have pixels for one image. That's 28 by 28, which is basically around 784. So we basically are going to take this 28 columns and 28 rows and make them in a single column vector of 784 input nodes. So to do that, we can start by, we don't need actually to predefine the array simply because we're writing it up the first time we define it, so that's fine. And then we're going to write that A input. So we're looking at which column we're at in the current row. Okay, so column 1, 2, 3, 4, 5. So that tells us how much we've done in the current row, right? And then we look at all we've done before that row. So it's going to be row minus 1 because we have to exclude the current one. Okay, row minus 1, and then we multiply that by so columns, current columns, and that's plus row minus 1, and multiply that by the actual number of columns in our image matrix. So that's gonna be, where is it? Number of columns. How do you write this up? Up, up, up. Okay, we're just gonna use size image. I thought we created a variable, but all right. So that's gonna be that one. Size images. Up. Here we go. And so after that's defined, we just say that, you know, there's only one column, so that's each row is going to be like that, and that's going to be equal to the current pixel we're looking at, which is basically at the current row on the current column and at the current image iteration, right? So we're looking at a specific image right now due to that for loop, and that's that data we're trying to extract. So we want one image per iteration. Obviously, each input node takes one image, looks at it, we do all the work on it, look at the next image, all the work on it, and at the end of all that, we do all the gradients and so on. One thing here, I forgot the S at rows, but I think we will both agree that it's not too important here. So once we finish this, we can then end the nested for loops. And the next thing we're basically going to do is start actually doing the forward propagation. So that's in fact quite straightforward because you've seen exactly what's happening through Albert's lectures, how that works. So let's go straight into it. We're going to look at, I'm just going to comment it now so we don't have to do it later. So it's going to be forward propagation here. And that's going to be, first we're going to look at the input layer. Obviously, we start from there. So forward starts from, you know, the first layer all the way to the end layer, the last layer, and then backwards goes from the last layer all the way to the input layer. So now we're going through the forward propagation. And so we're going to calculate the Z value, which is going to be a column vector. So it's going to have as many rows as input nodes, essentially, as nodes on the first layer, on the first hidden layer. And we're looking at the first Z, so basically for the first node, so not the input, the first node, which is going to be the first hidden layer, either the only hidden layer if you only put one hidden layer, or like the first of all the other hidden layers that if you put many more. And then we're going to have that that Z is going to be equal to the input weight matrix multiplied by the actual input nodes, and to that we're going to add the bias for the first node, for the first the first node of the hidden layer. The first layer basically. Sorry, the first layer of all the hidden layers. That's what I meant. So now we have our Z. We're basically gonna calculate our actual node value by using the activation function. So that's super easy. We're just using the function we created before, and it's activation of basically what we just calculated here. So that, and we're looking at the function we want. So we define this here, Leaky Relu or Sigmoid. And then we're also going to tell it whether we want it to be derived or not. So here we're simply going to type, we're not derivating anything, we're not differentiating anything, so we're actually going to use the standard Leaky Relu function, and then you can enter here. Just double check that the parentheses are okay. Okay, perfect. Now we've done that, we can now go through the hidden layers. Sorry, up the column here. Hidden layers. So that's gonna be if there's more than one, because if there's only one, we don't need to do this. If there's only one, then we actually just calculated it here. We don't need to do any more calculations. Now, as you remember, we only have W input and W output. We don't have any other weights to look at. But if there's more than one, essentially we're gonna have to do a for loop that goes through all the hidden layers. So we're gonna do a for loop that goes again through all the hidden layers, and that's gonna be, let's say, a L counter going from 2, okay? Because we've already done the first hidden layer, remember, so we need to start at the second hidden layer to the number of hidden layers. And now it's a bit tricky, but just try to picture in your head the actual node arrangement. The best way is probably to write it on a piece of paper to see how the nodes are laid out, where are the weights, where are the activation functions, where do they go, where are the nodes results, where are all the biases, the output layer, hidden layers, and all this stuff. So if you can draw out a representation of the neural network, it will really help you understand this part of the code. And basically what we're going to do is we're going to do the Z of each of these hidden layer nodes we're looking at. So here we're putting L, and that's going to be equal to the weight at that layer, because the way they're indexed, okay, because they're in between each nodes, they're not at the nodes. That means that there's one less weight than there are layers, okay? So you can just do -1 here. That's the proper way to index it. And then you can multiply that by the actual nodes you're looking at. So hidden layers, and that's going to be up -1. So here as well, essentially, because we're calculating the current node value from the previous one, right? So it's going to be the weights from, because of the index reason, we're going to do L-1, but we're also going to do AH at L-1 in terms of column, simply because that's going to be where we're calculating the current Z value from the previous node, okay? That's normal forward propagation like you saw in the theoretical lectures. So that's what we need. And here we can add the bias, and the bias is actually at the node, right? The way we indexed it. It's not the one from the previous layer, it's the one at that node. So it's going to be up L. Here we go. Let me just double check everything. All right, all good. All good. And then we can just simply do the activation which is going to be L equals activation up Z up. So we're just basically looking at what we just calculated, which is the Z at the current hidden layer, and then again function, and then here we don't want to differentiate anything, so we can end this here, and again let's end the for loop, end the for loop, and finally we can do our output layer right here, and the output layer is just going to be Z output. Again, because the output layers and the input layers have different amounts of nodes than the hidden layers, we need like different kind of variables and matrices to look at them separately. They need to be treated independently. So here it's simply going to be the W output multiplied by the last essentially node of the hidden layer, the last layer of the hidden layer. So that's going to be AH. So all these rows for the last node of the hidden layer. So remember, in case I wasn't clear enough about this, this basically means all the rows for that column, okay? That's all it's saying. Here, all the rows from that column. So we're basically every time looking at column vectors. And so here we're looking at all the rows for the last column of the hidden layer nodes, essentially. And then we're going to add the bias of the output finally to calculate the Z, and that's going to allow us to pass this through the activation function. Just copy paste that up. Activation function of Z output, and here the function we want to use, the activation, so it's going to be Leaky Relu, but could be Sigmoid if you change the value up there to 2, and that's going to be non-differentiated. All right, we're going to stop here for this lecture. I just want to comment a bit everything to make it a bit clearer. So here, what we're doing, we're essentially taking image data and attributing it to its respective input nodes. All right, so that's what we're doing here. There we initialize, I mean, that's just, okay, not that one, that's just like a counter for to know where we're at in the while loop, but that's initializing gradient and hidden layer nodes matrices up, and that's basically gonna be the loop that trains the network until we reach a satisfactory success rate. Sorry, up. All right, so that concludes this lecture. I hope this is all kind of clear. Little mistake here. Sorry about that, guys. Up. Anyways, like when we run the code in the last, we're probably going to have a debugging lecture because with all this, I might have done some mistakes that I didn't see. Maybe you guys even saw it, but I'll definitely correct it later. Don't worry. But yeah, that concludes the lecture. If you have any questions, please don't hesitate. All these kind of, different ways to look at matrices and call different parts of it kind of helps us calculate this fast in MATLAB, but it can be very confusing for our little brains. But yeah, the best way when you're confused is to draw out the network on a piece of paper and then just, place every kind of weights and gradients and actual nodes, biases, inputs, outputs, and so on. And that will really help you understand what's going on here. So as usual, don't hesitate if you have any questions, and then I'll see you in the next lecture. Thank you, guys.